All right, so welcome everyone to the second session of Tesseract Talks. My name is Jason, and I'm here representing FTC Team 21689, Team Tesseract, a community team based out of Nashua, New Hampshire. During this past season, Into the Deep, we ranked among the top 100 teams worldwide in OPR and delivered a strong performance at the World Championships. As we head into the new season, we're expanding our outreach with a brand new initiative, Tesseract Talks. This is a live webinar series where we sit down with some of the top performing FTC teams to go deep into one specific mechanism, system, or strategy that sets them apart. Every session is recorded and shared afterwards so people all around the world can learn and be inspired. Let me just share the presentation. There we go. So, for our second session, we're thrilled to welcome Team 12808, RevAmped Robotics. RevAmped had an incredible season, finishing with the 114th highest OPR in the world and competing strongly at Worlds and off-season events. One of the biggest contributors to their success, especially their incredible sample stacking, was their all-encompassing strategy. So today, we're diving into everything: early season principles, active intake, optimizations, drive practice, and more. At the end, we'll answer any questions, so if you have any, feel free to ask them in the chat throughout the seminar. So, first of all, going into the season, what were your first thoughts about the game?
Yeah, so when we first saw Into the Deep, we knew that whoever won would most likely depend on whoever put up the most yellow samples. This is because there's a limited number of shared yellow samples, and if we assume that both teams put up 20 specimens, the one that wins is obviously the one that puts up the higher number of basket samples. So we optimize our cycles speed for samples because whoever the one that puts up the more samples will be the one with the faster cycle speed.
Yeah, totally. That makes a lot of sense. And then, what kind of initial brainstorming and prototyping did you do coming into the season?
One of the first things we did, and this is something we do every season, is we look at similar years that have similar elements. So one of the things this year specifically was we looked at the team gluten-free during Rover Ruckus because the submersible was very similar to the crater element from that year. And that allowed us to look at some already pretty polished designs and gain inspiration. So that's where the first inspiration for our wide drop-down intake came from, and that was the what we ran up until the world competition. Um, and so our first design, it was very wide, had vertical rollers, the noodles to intake blocks, and then it had horizontal spinners that would align blocks in the transfer. And that was mainly done to limit our driver micromanagement because it allowed the drivers to really just go in and out as fast as they could. And like Levin said, we wanted to optimize our cycle time. So the less the drivers had to worry about how accurate they were in the submersible, the faster they can drive.
Yeah, that makes a ton of sense. It's definitely important to think about everything you'll be doing later in the season right at the beginning. So, moving on to game-specific decisions, why did you choose to main sample over specimen?
So
So
early
early
on,
season.
oh,
Oh, go ahead.
okay. So early season, we wanted a design that could do both. And that's what the original idea for our horizontal extension on the depot came from. But as we kind of iterated on our designs and as we just kind of built up the robot, we found samples were a lot easier and they ended up being a higher priority because we could optimize them further. And it worked out anyway because a lot of the other teams in our leagues were specimen bots. And so a lot of the correlation worked well anyway. Um, and it was also just more reliable and easier to kind of incorporate speed and optimization for, at least for us and the way we designed our robot.
That definitely makes sense. So, more specifically, why did you choose a two-stage horizontal and vertical extension over something like a pivot? And why did you choose an active intake over a claw?
So from the research we did, and we were inspired by teams like Cookie Bots during Power Play and Gluten Free during Rover Ruckus, we saw that double extendo systems usually have faster cycle times because you can both intake and depot. This matters a lot in like auto, right? Because for the preloads, you want to be able to score them as quickly as you can. We also didn't want to try to figure out pitching slides because we knew it was extra complexity, and we already knew how to do double extendo from years like center stage. We chose an active intake because we want it to be very, very easy for drivers, as Tanner said. Um, we really wanted to avoid really accurate driving because that's a problem we had last year during center stage, as we had a very thin intake. The active means that drivers can sweep through the submersible, and auto sorting in the intake will do it for them, meaning that they don't even need to think. This means that they can make the cycles faster because a lot of the time is spent optimizing the depot, not just the intake.
Definitely. All right. So moving on to optimizations, how have your designs and archetypes changed through iteration over the course of the season? So what optimizations did you make, different design choices, and when did you choose to redesign mechanisms entirely? And then after that, what specific optimizations have you made to improve performance?
So, one of the main components that we worked on optimizing and iterating on throughout the season was the intake. It's been through numerous variations. So, we noticed that the first like generation of intakes, the wide ones that we had, they would get stuck on the samples a lot because they couldn't really force their way down. And if there's a heavy like area of samples, they have issues getting into the submersible and actually intaking. So that was we were losing a lot of time on that. And we also couldn't intake anything that was too close to the edge of the submersible because the intake will get stuck on the barrier instead of, getting those samples. And that slows our cycle times a lot because drivers need to worry about moving around and forcing the intake down. And so that's why we put the virtual four bar on the intake. And that allows us to angle the intake straight down. And so we can either intake from the submersible wall or it just gives it a little better ability to force its way into the submersible. And we have selection modes in our driver control period for vertical intake, which will almost like the ice robotics intake. It'll go straight above the sample and try to intake them without getting fully onto the ground.
Yeah, totally. And talking a little bit more about that vertical versus horizontal intaking, why do you have both? Is one of them more optimized than the other, or do you just have them for versatility?
I mean, the main goal is versatility, but one of the reasons we decided to go with this was because our deposition is very complex, which means it extends out the back of the robot a lot. And because of the 42-inch extension limit this year, we wanted to optimize how much area of the submersible we could reach with our intake. And so some teams do that by making their horizontal extension much longer, and that allows them to reach farther. But because we couldn't do that, we decided to try to reach things that were too close for most teams to get. And so that's what the original idea for the virtual four bar was because we saw teams, other teams do it as well, and it allowed them to grab from the barrier of the submersible. And that really helps because our drivers have that extra ability when most other robots don't. And usually those samples aren't being touched by anybody because nobody else can reach them. So that kind of gives us things that only we can do in a game, which is pretty good.
Yeah, 100%. So moving on to specifically talking about your deposit, I think we already covered this a little bit, but why having that horizontal extension on the deposit initially?
So initially, we wanted the ability to do both samples and specimens, as we mentioned before. And this horizontal extension allowed us to pick up the specimen from the wall and then deposit them without like making major adjustments to our robot's heading, for example. And it worked really well on our version 1 robot, as you can see with the horizontal transfer, but it didn't work as well with the vertical transfer, as we saw at Worlds. So going into MTI, we decided to remove it and focus mainly on samples.
Yeah. And then why did you add a turret on the deposit and then subsequently remove the extension?
So the original turret for our world's redesign was for the specimen because we knew our sample game was pretty good and that our specimen game was really going to be our setback overall. And so the turret idea, similar to teams like Theseus, was to angle the specimen at a 45-degree angle, which allows the robot to stay in a straight line the whole time, especially during autonomous. This makes the scoring of the specimen significantly faster. And if you're trying to go for those 6 or 7 specimen autonomouses, that really matters because you need to be as fast as possible. But then what we saw at Worlds, similar to the horizontal extension, was it just led to a lot of issues with inconsistencies. And the turret had to be lined up perfectly to travel through our vertical slides on that horizontal extension. And we had just had so many accurate timings that it ended up being almost impossible to keep everything perfectly in sync. And especially even things like the voltage changes or speed, all that can affect how your things are going to line up. And that makes it really difficult to have consistent transfer, consistent scoring. And so we took that off. And then when we removed the horizontal extension, we kept the turret on our MTI depot. But at now it's mainly used for the sample autos, especially the three preloads on the ground, because it allows us to always keep our intake pointed at those samples. And like Levin said, with the dual system robots, you always want to be intaking the second you drop the sample off your depot because that's just going to be the fastest way. So we kept that turret so that we can depot and intake almost simultaneously.
Yes, and then with that turret, do you achieve the full horizontal extension limit as well as the vertical or well, in the horizontal extension box, do you achieve the width with the turret?
That wasn't our priority for us. It was mostly just to do the angling, but I'm pretty sure we do almost get there.
Yeah, okay, yeah, that makes sense. All right, and then next, you guys have some really, really fast slides. So what optimizations did you make to achieve that speed?
So from a mechanical standpoint, our lift ratio off bare motors is about 1875 on 30 millimeter spools, which means that our lift had a very high speed but very low torque. So, this is really good because you want your lift to be obviously fast, right? But without that torque, you can't accelerate that fast, and it ends up being a bottleneck. So what we had to do is we had to counterspring with a system where a lever arm pulls string that pushes up the slides. This means that the lift motors have to do less work and the slides can accelerate up better.
And for your counter springing, do you guys use perfect gravity counter springing so the lift stays still everywhere, or is it just helping where it's needed most?
Yeah.
It
So,
isn't,
oh, Levin, you go.
yeah, it isn't perfect. Like if we put it up to the highest position, we don't have as much spring there, but it's still helping. So mostly it's for the like initial acceleration phase.
Yeah, that makes sense. It's definitely important to not only achieve that high speed, but get up to it as quickly as possible. So, moving on to your driving and teleop, one of the most impressive things about your robot, especially later in the season, is your ability to stack well over 25 samples into the high basket during a match. So, how many do you get, and what optimizations did you make to do that many?
Yeah.
Yeah,
So
so
like Levin mentioned a lot, we really wanted to prioritize the stacking. And what we did in our very early kind of testing was figuring out which configuration of samples in the bucket is going to be consistently the highest number. So what we found is if you throw them randomly, you're probably getting 18 to 20, which isn't bad, but if you really want to push everything you can get out of it, you need to have optimized stacking that's consistent. And so what we did was we put a wrist on our deposition claw. And what it'll do is orient all the samples 90 degrees so that they are parallel with the bucket. And they kind of make like this grid pattern. And we found that to be a significantly more kind of dense method of stacking all of these samples. And we also have two positions in our teleop. So for speed, our first position has the arm as high up as it can go. And what that means is the slides don't have to go as far. And that's just going to be faster in general. And when the bucket is reasonably empty, it is it's going to be faster because you don't have to worry about your placement because the chances that a block's going to fall out is really low. But when that bucket starts to fill up, then we switch to a more vertical position. And that's when the wrist is being used to track the heading of our robot. And Pavish can talk about it, but we use our pinpoint sensor to track the robot's orientation on the field. And that kind of autonomously spins that wrist so that it's always lined up with the bucket and our drivers don't have to do any like manual control on it because that's just going to give them more things to think about. And when you're trying to have 4-second cycles, they don't have the time to really worry about things like that.
Yeah, that's definitely one of those small optimizations that makes a really large difference in the ability of the drivers to cycle super fast. So another question that I have is when you're going to do that stacking in the high basket, especially once you're getting towards the end of the match, do you do any manual adjustment of the arm, or is it just that heading control with the wrist?
So the drivers do have the ability to have manual control of the turret and the wrist, actually. Usually it's just in increments of 90 degrees because that we found to be the main differences, especially if you're trying to create almost like a pyramid in the bucket, kind of, because that's how you're going to get the most height out of it. But yeah, so if they need to, they can, and the drivers will work, they'll coordinate where they think the best sample placement is, and then the drive coach also helps with that, figuring out, where do we think it's going to be the most effective and how are we going to optimize placement in the future as well?
Yeah. So moving on to your drive practice, how much have you done this season? Because you have such an amazing teleop. And then how do you perform your drive practice? And is there anything that you consider that you do as special?
Yeah, we think drive practice is really important. So we do a lot every single day, about 1 to 2 hours. Mostly it consists of like 2 minute full teleops to prepare our drivers to do the same on the real match, right? So this gets them like used to the robot. They know what the robot can do, and they can work with each other to be better when, during high stress situations. I think the main thing we do differently is that we really, really, really try to pick apart every part of the cycle. Like if we see something is going slow, then we can either make a mechanical change or we can tell our drivers to change something that so that it's like removing a bottleneck. Because we really do want that super high cycle speed. This is what it takes because we have to remove every inefficient action in our cycles. Um, we don't do a lot of defense, but we have tried it because we're not really a robot that can shove. We're not like Turbo V8, which can like bulldoze anybody they see. So a lot of things we try to do is we have our teammates run our old robot, and then we can try avoiding them. So that means we can go to the short side where the specimen bot is, and alternate between that and the long side.
Yeah, that makes sense. And then I know you talked about some of the small things and bottlenecks in your cycle time. Can you give an example of one of those that you encountered and then how you fixed it?
Yeah, a really like prominent example is probably our intake. So with our old intake, it was that like the wide intake, right? And then we had to spend like there were cycles where we had to spend like 2 to 3 seconds just jamming it onto the ground, and we knew that that wasn't acceptable because we wanted the fastest, right? So that's why we switched to the four bar. This means like the four bar can easily get into the submersible because it's like a small surface area and it doesn't get stuck. Yeah.
Yeah, that's definitely awesome. So, moving on to your autonomous and your software, what optimizations did you make for autonomous mode to ensure you could get the most samples and then earlier in the season, the most specimens? And then, do you have any specific teleop enhancements that you think are really innovative, like your wrist or something else?
Yeah, so last season we actually did our autonomous with Roadrunner and we found it to be like not optimal in terms of speed, and it was kind of inconsistent too. So this season we helped develop padropathing. So it's an alternative to Roadrunner, and it's an autonomous software path following library. Um, it's optimized to go at the robot's maximum speed capacity, and essentially it has very fast deceleration. So that's something it does better than Roadrunner. It has more control over things like heading interpolations, as well as very strong corrective capabilities, meaning that if the robot gets knocked off the path, it can correct back onto the path, as well as stay on the path using its centripetal force correction. Um, we also tested out the Go Build a pinpoint sensor, and we found it to be a lot more accurate than three-wheel odometry. So we helped to implement this into the pedropathing library. In terms of teleop enhancements, um, so I think that uh, auto aligning on the wrist was really helpful for our stacking. So we used the pinpoint sensor and inverse kinematics to align the wrist to the basket, and this helps our stacking quite a bit. Um, Also, we found it really helpful to be able to automate actions, but we also automated like transitions, and we had it so like if the drivers press a button and that transition is illegal, then it doesn't perform that transition. And essentially what this gave us was the drivers can like press wrong buttons and things accidentally, and the robot won't kill itself. So this simplifies their task.
Yeah.
Yeah, and then I was going to speak on the autonomous optimizations for the mechanical side. One of the things we implemented going into MTI was we added ultrasonic sensors to the front of the robot. Because one of the things we found in our autonomous was when we're traveling from the bucket after doing the four preloaded samples on the floor into our submersible, it often would either overshoot or undershoot the path, or we would find ourselves not quite lined up with the submersible. And that caused a lot of issues because you would either have the intake will drop and it will get stuck on the barrier, or the robot will never complete its path because it gets stuck on the barrier itself and can't reach that position it's trying to go. Or even if we're not lined up, we might extend into the other team's side. And that obviously is really bad because you don't want to get penalties or mess up their autonomous. And so what we do with these ultrasonics is it allows us to figure out how far away each side of the robot is from that submersible barrier. And then we can correct using that so that we're always lined up at the same spot. And because our autonomous does not use camera vision and it's all blind, that really matters because we need to know where we were so that we don't accidentally try to intake from the same area again, because then there will be no blocks there. And that makes it difficult.
Yeah, so because your autonomous doesn't use CV, how do you go into the submersible and find samples, and then how do you ensure that you have the right one before moving on?
Yeah, so that's one of the benefits to the virtual four bar that we found is what we do is at the start of every cycle, we will reverse our intake and actually clear an area in the submersible. And that gives us an area where we know there's no samples and we can always drop the intake, which gets around the issue we had previously, which get with it getting stuck on the top of samples. And then from there, we just run the horizontal slides through the intake through the submersible, and it just searches every time it intakes a block. The color sensor detects what color it is. If it's one of the colors that we can intake, whether it's a yellow or our alliance color, then it'll do its transfer and it'll go deposit. If it's the wrong color, it rejects it through our trap door, and then it keeps going because our intake has pass through ability.
Yeah, I love that. It's definitely sometimes when you have an active intake, it's a lot easier instead of implementing CV to just go in blind and use some sensor vision to ensure you get your block. So that wraps up the presentation portion of our second episode of Tesseract Talks. So for any of you in the audience, if you have any questions at all regarding Revamped Robotics' strategy or other parts of the robot, ask it in the chat, and then if time permits, they'll be answered. We did get one question that was pre-submitted, which is how do teams get old parts easier, and what are common mechanisms that can be used between different seasons?
Yeah, I mean, for the answer, like, how do we get old parts? Usually we try to reuse parts that we already have, so we don't need to spend excess money. And like common mechanisms that we saw were double extendo. Like that entire system is very, very versatile, since every pick and place is usually achievable by having a horizontal slide and a vertical slide.
Yeah, that makes sense. So we did get one question in the chat so far, which is how does pager pathing? Oh, now we got three. So how does pager pathing decelerate, first of all?
So essentially, pedropathing calculates a stopping distance based on kinematic equations. It calculates where the robot needs to start decelerating. And before that, it'll keep going at full power. And then there it starts to lower its target. So using the kinematic equations, we calculate what the initial velocity needs to be, such that if we like stop our robot, completely brake, it'll land at the target spot. And then we use that as our target velocity, that calculated velocity, and we essentially run calculate the drive error based on our current velocity and the target velocity. And using a Kalman filter, we're able to smooth out noise on this estimate. And then we use a PID to calculate our drive power.
Yeah, that's definitely a really good explanation for that part of page pathing. So our next question that we have is what strategies made your team successful? So I'll let you take this in whatever direction you want.
I mean, I would say on the kind of robot side of things, it's definitely um, we do some things like parallel design. So especially early season during our prototyping phase, everybody will work on their own mechanisms and design, and that way we can test, five different types of intakes, for example, all at the same time. Whereas if you kind of go one at a time, you slow yourself down a lot because you can only test one when you finish the other. So that's one for the mechanical side.
Yeah, definitely. And then I have a question just to add on to that. Is there anything special that you do from the team management side in terms of like communicating and assigning tasks?
Um, yeah, and I think Pavish could also talk about this, but we use Discord for our team mainly, and we kind of split into subgroups. There's obviously the three main. We have programming, we have our build, and we have our outreach. But even within that, we can split up even more. So we have leads for the build, and they will work with a small group of people, like two or three people. And that way, it kind of makes this hierarchy where it's not one person who has to manage all 20 people on the team or whatever. We kind of split up the work. We can delegate things, and that just makes everything go a little bit faster.
Yeah, my team does something similar with figuring out like what are the important tasks that need to make their way up the chain of command. And then it's just definitely really similar to how things work in the real commercial world. So we have one last question. And before I ask this one, if you guys have anything left, we just have a few minutes left in the meeting. So if you have any additional questions, please feel free to ask them now. So the question that we have is, how does your in-season design process work, and how do you guys test prototypes and then iterate upon them during the season?
Yeah, I mean, our season design process is pretty general. It's like you brainstorm, we come together as a team to brainstorm about the season challenge. We think about ideas and like we research like mechanisms in the past. Our philosophy is like um steal the best, invent the rest, right? So if it's already been done before and it's been done well, we'll try to take that and we'll try to implement that. Um, so for the prototyping, we really we spread out as a team to prototype which means, oh, I mean, testing prototypes. Yeah. So basically, for example, like an intake, we can take a drill and we can power it like we can power the rollers. This means we don't need any fancy wiring. We can just take a drill and then shove it into the submersible. We look at like if there's any like potential points of failure or any like big flaws to that intake, and then after that we can iterate by improving those flaws, or we can skip that design entirely and move on to a separate design.
Yeah, that makes sense. And then this is a question that I have that my team does, and I know some of the other teams I've talked to, like RoboKings, do as well, which is on like initial prototypes, we add like go build a pattern into it or a specific hole pattern to allow like the movement of different parts just a few millimeters at a time. Do you guys do anything like that?
So we primarily solve this using CAD, but I really would like to emphasize that having accessibility to move things around is really, really important. Because early season, you don't necessarily know how your robot's gonna look like, and you need that flexibility to change your robot up in case you need like a special task. Like for example, level three, if you had the like if you had the accessibility on your robot to add like a level three mechanism just straight on, you could screw it in. That makes it a lot easier.
Yeah, definitely. So the last question that we have for today is with so many motors and servos on your robot pulling voltage and power, how do you guys ensure that you don't blow any fuses when you're pushing against other teams while cycling or just generally in the match when you're running so many mechanisms?
Yeah, so actually in the competition we try not to push against other teams that much. That wasn't really part of our strategy this season because basically our philosophy is our robot is very optimized for scoring samples and pushing against other robots is essentially time that we spend not scoring those samples. and we like to think that we're one of the fastest scoring robots um, on the field. So we want to score as many points as we can, and we think that's more that'll get us more points than blocking other teams. It'll be more likely to maximize our winning capability.
Yeah, 100%. So, thank you all so much for attending today's Tesseract Talks. We hope you found this explanation of Revamped Robotics robot and strategy helpful and gained some more insights for when you design your own subsystems. Huge shout out to Revamped for their time, and we hope to see you back for future episodes of Tesseract Talks. Thank you guys.